Hi, and welcome to Simplifying Disaster Recovery with Delta Lake. We're going to talk to you today about how Delta works, what can happen with respect to Delta and cloud replication, and we're going to run you through some simulations and solutions for issues that we discovered with Delta Lake and disaster recovery scenarios, particularly with respect to cloud replication. So my name is Zishan Papa. I'm a senior solution architect with Privacera. We make Apache Ranger in the cloud. I've been working with Apache Spark since version 1.4. I used to be an enterprise architect with Avanade, and previously before that with Teradata. I've consulted for a number of firms across financial, insurance, tech, and pharma.
And hi all, my name is Itai Wise. I'm a senior solution architect with Databricks. We make your streams come true. I've been working with Spark since version 1.6, and I've been consulting for big data and data warehouse project across many verticals such as financials, insurance, tech, pharma, and others.
So one of the things I'd like to talk with you real quick is a bit about Privacera. The way that enterprises have traditionally dealt with data access control was in a siloed database by database, platform by platform, user by user approach, which worked in a pre-hybrid cloud world, if not an ideal situation. But today, in today's world, it's completely untenable. With so many heterogeneous data and analytics services in use in the enterprise today, both on premises and in the cloud, and simply so much data flowing into these environments and so many different users to manage. That siloed approach is too much labor, too time intensive, it doesn't scale, and it also makes it very difficult to identify and tag your sensitive data at scale, and then to monitor and report against user access behavior across those silos. This leads to inconsistent policies for the same users and roles, depending on the data service. As each service has its own access control capabilities, some better than others, enforcement is largely manual across each of these services. So on the left, you see a pre-Privacera world, and on the right, you see a scalable compliance in your hybrid cloud environment powered by Apache Ranger. So Privacera's primary use cases are, at least in terms of what we're seeing consistently out of customers. And when it comes to customers, we're at multiple Fortune 500 and multiple Fortune 100 companies. And while all of our customers are individually unique, we've identified these three as kind of common initiatives that companies come to us when looking for a solution. First, we hear that companies are trying to migrate from on-premise environments like Cloudera, Hortonworks, or MapR. We also deal with a lot of companies that are trying to achieve some kind of regulatory compliance with the cloud. And then we also deal particularly quite a bit with the data democratization use cases, which is I want to have and give my users the ability to have access to the data that they need access to in order to make the best decisions and have the best insights, while at the same time making sure that I'm achieving compliance and applying consistent data governance. With that aside, I'd like to talk to you a little bit about the problem statement today, how Delta works, what exactly is going to happen or could happen in cloud replication. Then Itai and I will simulate the problem and talk through some problem resolution options, as well as demo some solutions for you and discuss future solutions. So this is kind of the crux of the problem statement. So although the Delta file system itself caters towards disaster recovery use cases, because of the nature of it, when we combine it with cloud replication, there's the possibility of our Delta table being corrupted at our DR point, which of course would hinder or outright delay, possibly stop you from doing entirely your RPO for your mission critical workloads. So there's multiple things to consider here. When you come to options, right, the first and foremost is you can certainly wait for the problem to resolve itself. Most of the time with most clouds, storage failures are intermittent. Most clouds have extremely high durability, usually in the 9 to 11 nines. You're looking at this being usually in most cases intermittent. But if you have mission critical data, you really don't have much of an option. And if it's time sensitive as well, you have to recover to a previous working version in your replicated instance so you can continue. There's a couple of different strategies there as far as how we would resolve the problem. The first is, can you actually query the table? And if you query the table, chances are it's not corrupted. But if you cannot query the table, then you would need to find out which process ran since the last recovered version, and then effectively batch, whether it's a batch or a stream process, you'd have to rerun the processes in order to basically recompute your data to get back to your desired state. So in order to kind of understand why this is important, something that we feel is a very key precursor is to understand at a very high level, at least, how Delta itself actually works. So when you create a Delta table, it effectively looks like this on disk. Your root directory is, say for example, my table, and underneath that you'll see a little folder called _delta_log. So that is what is called the transaction log directory. So this basically identifies it as a Delta table. Underneath that directory, you'll see 0 to L max value. So that integer number there is actually a long rather, and it'll go to a long max value for all the table versions. So this is basically metadata that describes and identifies all of the versions of the table. Separately, you'll see any partition directories and the underlying Parquet files that are underneath them. So for those of you that aren't aware of this, Delta actually utilizes open source Parquet. So these files, like for example, that file-1.parquet is actually readable. And it's readable itself with any standard Parquet reader. However, in the context of your actual table, and when you combine it with the metadata that's generated from the Delta log, Delta overlays, which is effectively an access or a read pattern for the data that tells the Spark reader which files to read, what version, which files to skip, so on and so forth. So as you can surmise, that Delta log directory and those small files that exist in there to describe all that metadata are very key to how Spark is going to read and write to your table. So a little bit about Delta JSON files. So I think a reasonable way of looking at this is to just talk about add, remove, and set transactions. So these JSON files have a variety of different actions, which are effectively things that can happen or things that are described as having happened within those files. And the most common ones are add file, which would happen in an append operation, for example, where a new file was added to your file system. So you say you had a new file or an updated Parquet file, you would see an add file event in one of those version files. Same thing with the remove file. So say a file was deleted or compacted, you would see that record in the version for that that corresponds to that action. And in the case of set transaction, this is a recording of the idempotent transaction ID for streaming use cases. So it literally would contain the ID of the stream that lives in your checkpoint metadata, right? So these are things like epoch values, number of batches, stream identifiers, so on and so forth. So all that data is actually stored within the Delta log directories, and you could absolutely go and inspect it yourself if you're ever curious as to how that works. So just to be 100% clear, if I was to do, say, a df.mode append save, right, I would expect a Parquet file to be created underneath. I would expect that a corresponding Delta JSON file would be added with an action in there that signified that I added a Parquet file named part whatever it was .parquet. If I was to do a delta table.delete using the Delta IO APIs, I would effectively create a new Parquet data file without the deleted data, and then I would create a Delta JSON file with a delete reference to that file, and then an add reference to the new file. So the reason for that is that Delta implements Atomicity. And because of that Atomicity that Delta is implementing, this is to support ACID transactions and to support multiple readers and multiple writers. In order to do that, though, changes to the table are stored as ordered atomic units called commits. And in order for Delta to be able to support multiple readers, we can't delete Parquet files if they're deleted. We have to keep them around for some period of time so that any readers that are currently reading that data can finish their read operations. So let's just talk a little bit about how these commits work. So let's say, for example, I have one commit 0000.json, another commit 01.json, and then another commit underneath that. So in the first JSON file, I've basically created two Parquet files, and that happens as part of the first version. In the second version JSON file, I've removed 1 and 2, and then I've added 3. So what ends up happening here is that if I read this table and I look at this directory, and the Spark reader reads this the sequence of these metadata files, it'll effectively skip over 1 and 2 and just know that I only have to read 3.parquet. So, all right, I think we have hopefully by now a pretty good understanding of how Delta is working. I think the next place to start is to understand, okay, I've got all these small files, I've got all these big files. What can happen in cloud replication? So a good level set is to understand what is cloud replication. So in cloud replication, you have data stored in multiple data centers or cloud provider regions. This is something that's offered as a feature of underlying cloud storage, such as your AWS S3, Azure Blob. And the intent here is to ensure consistency between primary and secondary regions. So how does cloud replication help in DR? Well, most obviously it helps in meeting your compliance or high availability goals. And it also, as part of other application level DR components, helps you deal with your DR objectives in terms of being able to have and hold to your business continuity plans, however they might be laid out. Most options with cloud providers allow for variable types of replication options. Multiple copies can be stored in proximity or very far away from each other with things like minimum distance guarantees. So there's lots of ways in which you can utilize cloud replication to help you with DR. Now, the two kind of high level, at a very high level, there's two kind of big major differences in the way most cloud replication products work. So you've got inter versus intra-region replication. So inter-region replication is where you have one region that syncs to another region. So this could be, I've got a region, say East US 2 in Azure, and I'm syncing my data down to Central US in Azure. So these are two physically different geographical regions. And this is really good for disaster recovery use cases because, if there's a disaster that happens, it's a lot of times we're planning and guesstimating for these disasters to happen along regional boundaries. It's a safe bet that region 2 would still be available in the event of some kind of a failure at region 1. In the intra use cases, right, these are kind of more fit for high availability use cases, and this is where you would have availability zones within a single region, and those your data or your applications would be synced or synchronized and replicated across those availability zones. What we're mostly going to talk about today is inter-region replication, and we're going to try to just understand very briefly what that anatomy would look like. So let's just walk through this example. Right? A user, Databricks or Spark, would write data to a cloud storage device, whether that's an ADLS account, a blob storage account, so on and so forth, or an S3 bucket. Those writes would happen in parallel from each worker node to each partition. And then Spark is also responsible for writing that Delta transaction log. So when that data lands at the first region, it's written to that one region, of course. It always goes to the one region first. And then data is now replicated locally or cross-site, depending on your cloud provider settings. This is generally an asynchronous operation. So data is replicated asynchronously to the second region. And by virtue of being asynchronous, it's replicated in a non-deterministic fashion, which means there's no strict order guarantees, which means that larger files can take longer to arrive. So I think that's the deciding point here, right? With the Delta file system, we have a lot of large files, which are Parquet data files, and we have a lot of small files, which are your table metadata. So how does Delta help disaster recovery? I know I mentioned this earlier, briefly covered it. The Delta log, at the end of the day, this is 90% of the way there, right? We're capturing the last write and delete transaction that's committed to disk as individual versions, right? So this identifies every time we write to the table or make any changes to the table, we have a record that specifically talks about the data files that were related to that transaction. So this is great with DR because this helps us in understanding things in an ordered and predictable way. And we can clearly understand based on the log files, based on the log, what files might be missing in the case of a disaster recovery scenario. So that gives us at least the ability to safely and predictably roll back to our primary region. And the bottom line is that Delta is the best big data format that allows for reliable disaster recovery on the cloud. So Itai, can you walk us through what could happen in a DR event with Delta?
So thanks, Zishan. You did a really good job explaining how Delta works and how the cloud replication work. And yes, I agree with you. In some cases, there may happen a potential failure of the synchronization, or it's actually the asynchronization order in which the data files and log files will arrive to the secondary region. And if we simulate it, on the left side, again, we'll have a user or a job writing data using Spark. The first thing will be to write the data files. Once this is complete, if there is no any collision, a commit will happen, which will write a log file. Both of those will be committed on region 1, and in a way start their transfer towards region 2. However, since the data files is usually much, much bigger than the log file will be received in region 2, and if something happens, the data files will not end up in region number 2. In this case, we will have an out-of-sequence replication. In region 1, we'll have both the data files, parquet 00, whatever, and the JSON file explaining that this parquet is related to this version and contains this data. On the second region, we will have the same JSON file indicating that the version has been committed, but the data files will not make it and will end up with either partial file or no file at all. This can cause a problem. And for example, this is one of the problems. When the file will not be found, we can see that Spark is unable to read the delta file or the delta table. Will generate an error saying the data file does not exist. So the big question is, how do we use delta to fix this scenario? We're going to simulate the problem in a notebook, and then we're going to run 2 notebooks with 2 separate solutions. When we're back, we'll summarize these, and then we'll go over and look at what are the future solutions. So here we break for the first video recording of Zishan.
Thanks, Itai. So before I dive into the rest of the notebook, one of the things that I want to talk about, again, just to reiterate and drive these points home, is what problem is we're trying to replicate here. So in the case of disaster recovery with Delta Lake, if we have one region like we have on the left and another region like we have on the right, and we have some asynchronous replication process as part of the cloud provider's offering that is syncing this data, what is possible to happen is that this manifest file that you see here on the left could arrive here much faster than your data. Because it's much smaller than your data, and your data may be very large, right? Certainly greater than a megabyte, and certainly less than a megabyte in terms of the actual manifest. So if that in this time that this file is replicated over, and this file doesn't make it, and you know, in the event of a storage failure, right? Now what you have is this corrupted table. So what we're going to do is we're going to go ahead and recreate. And run some data here. So we're going to use the bike sharing data set from the Databricks data sets for this example. So we'll start by reading it into a Spark data frame from a CSV file. We'll filter out data from 2011 and write that into a table called bikes. And then we'll also filter out data from 2012 and write that into the same table. So we'll have 2 adds and 2 versions in our table. So here's that data and what it looks like right now. And now we'll take 2 filters of that data out for these time ranges and write them out into our table. And because these are 2 different save commands, they'll result in 2 different commits and 2 different versions to that Delta table. Now we'll create some metastore entries so we can easily query these using SQL. And just a quick test, everything should be okay. Looks good. If we were to use the describe history command on this table, what we'll see is our 2 append transactions. And you can see here operation parameters mode. And then you can see, if you dive it even a bit further, you can see the number of output rows for each of those appends and the number of files that were added into those into this Delta table. So what we'll do now is we'll create a secondary disaster recovery table that's basically a copy of this. So this is effectively analogous to what's happening with your interregion replication, right? You wrote your data to your region 1, which is the bikes table that we just created above and queried. And now there's going to be some asynchronous process that's going to happen behind the scenes to synchronize that data at a file level to matching accounts within region 2. So we're going to do that, simulate that with just a copy command. And then create any necessary metadata entries for that. And we'll see that we see the same two transactions as we saw in the previous table. This is exactly what we would expect. And if you were to go look in the Delta log for either of these tables, what you'll see is version 1 and version 2. We can read in each JSON transaction into a data frame to see what's actually logged. So this is the actual data that's inside each of those commits, right? So this includes the number of records. This includes data about the file name that's written down to, and it also includes the name of the name and location of the Parquet files as well. So if we wanted to see what the latest version was, the latest transaction, we can run this little code snippet here, which is basically very simply looking in the Delta log folder and grabbing the latest version where add is not null. So this is basically the latest add version of the table. So that's it right there, 001.json, which is what we would expect. And then we can see here the Parquet files that make up that version. So that's the actual physical file on disk that refers to that latest version. And there's two that make up the entire table right now. So if we were to query that, you'll see that there's two files. So the latest version is this 968, and then the 2E26 is the version prior. So Itai, let's take this and let's move over to your solution and see if you can explain to us how these corrupted transactions, if we were to actually corrupt a transaction, how we could correct it.
Zishan, this was a really good notebook. Now we have data ready and we have two tables, a regular table and a DR table. And then let's use it to simulate. Looking at the solution, first of all, we'll have to check the last version, right? Is it corrupted? There is a good chance if we didn't have any write recently, or maybe everything worked fine, maybe the S3 didn't fail, or the ADLS or blob replication, everything will work, we don't have to worry about it. But if we do find a problem, then in the first solution, we will rename the transaction log entries in a way this is an undo of the last transaction. We will tell Delta to ignore it by the fact that Delta will not recognize the log files as they used to be. We'll then clear the cache to make sure that we don't have any leftovers in Spark memory or in our Delta format. We will rerun the last job. So we will go back and recreate the same last version under the same version number. So if we have a version 1 corrupted and we renamed it so it doesn't exist anymore, we're now recreating version 1 again with the right data. And then the table will be ready for us to be able to use it. So then we can run the new jobs, let the users use it, or basically continue business as usual. Let's look at it in practice and let's go over the notebook and understand how this renaming works. Let's look at the first notebook. This is the first solution where we're going to undo the corrupted version. First thing, let's look at the tables that Zishan prepared for us. The first table is our original bytes table in the primary region. Everything looks fine. We have two versions with the timestamp and created by Zishan. And let's look at the DR table. Yes, it is on the same region. It will be on the secondary region in DR, but we have exactly the same versions written by Zishan, same thing. Let's see if the data works on our DR. So we'll query it quickly. We can see that we have two different records as expected. If you remember, 2011 was created as V0 and 2012 was created as V1. Let's look at the files and let's make sure that we have the same Parquet files, one per each version that we've seen before. And we can see two Parquet files. These are the data files and the log files. We will simulate the corruption of the latest Parquet data by version using a code. In a way, we'll identify the last file, and then we will delete it using the dbutils array command. And now let's try to query the data and see what happens to our assumption. And in a way, as expected, we found that we got an error reading file on the same Parquet files that we did after that. So we successfully simulated the DR corrupted data file. And now let's find out if we can fix it. We create some Python functions that will identify these file names, sorry, the transaction file names. We have two, one of them is JSON and one of them is CRC. And then we'll create a function that will allow us to roll back to a specific version. You will be able to find these notebooks as well as a session under the Summit archive website. And for now, we're just going to rename them. Here is the CRC file named to CRC rollback, and the same is the JSON. We'll clear the cache just to make sure that nothing that we try to read will go back into the Spark cache or Databricks cache. Try to find files that don't exist anymore. And now let's describe the DR table history. We can see that we have only version 0 in here. So we successfully rolled back version 1, the corrupted version with a missing file. Let's try to query this v0. Using the time travel mechanism, we can query bike dr at v0. We can see that we got only the data from the v0, which is the 2011 data. Since v0 works and we can query the data, let's rerun now the same version 1. We'll populate the data for 2012 again. And now when we query the data, we see that now we got back 2012 data. So now the table is complete the same way that in matching the same tables that we have in the primary region with both the same amount of records for both here. Let's take a look at the delta log directory. And we can see here that we have version 0 CRC and JSON, version 1 CRC and JSON, but we also have a notion of the version 1 CRC and JSON, which is rolled back. So now it's very easy for us to see that version 1 was recreated and we did roll back it. And if we ever need this data for the rollback or any other audit purposes, we'll be able to find it. Let's go back to the slides and look at the second solution.
So this was solution number 1. In solution number 2, we'll check the same version. However, instead of renaming the version, we will override the data files, in a way nullify it. So think about it as, I really don't want to change my data log, but I know that I have an option to overwrite my Parquet files. I'll empty them, so I'll have an empty version. Then I will clear up the cache. I can now rerun the last job. I will still have the corrupted version. So again, if version 1 was corrupted, version 1 will stay there, but will become empty. And I will create version 2 as a new version that is similar to version 1 in your primary region. But once we're done with this, then the table is ready and I can continue business as usual and open up the table for the users. And let's see it in action.
Let's take a look at the second notebook. This is the second solution, override corrupted version data files. First, let's disable cache because we are going to play with data files. And then let's look at the history for both the bikes table and bike DR. Just make sure that we start fresh. We have two versions for the bike table on the primary region. And let's look at the DR table. And as we simulated, we have the same two versions on the bikes DR table. So everything is fine. Let's query the data and make sure that it is operational. And just like before, we can see that we have two records, one for 2011 from version 1 and one for 2012 for version 2. We look at the data files, just making sure again the two Parquet files and the delta log. We'll use different methods, but in this case, we'll find out the latest file. And right here, we'll find the latest file and remove it. Same way we did it before. Great, we'll check. Just like before, we're supposed to get an error right here. It says that we cannot read the file that we just deleted, and we just got the same error. We simulated again and missing Parquet data file in the DR.
And now let's find out how we can change this. So first thing we're going to do is look at the DR table and find all the JSON, and from there we'll find what is the latest version that we have. And we can see that version 1 is the latest version. We knew that, so that's not a surprise. But now let's find out which Parquet file are associated with this. You can see that version 1 has only this Parquet file, which is the same one that we removed before. We also logged the latest stable version, which really is the version that we're going to use to overwrite version 1 files schema. Now, let's make sure, first of all, that version 0 really works. Using, again, delta time travel, we bring the data, and we'll see that we got only the year 2011. The table works with version 0, so everything is fine. Next, we'll read the schema from version 0, and we'll store it in a variable. We'll then create an empty data frame. We'll create a new Parquet file in a temp location, which is an empty Parquet file. We'll ls it, and then we'll copy it over in a loop for all the files that are part of the latest version 5 that we found out about. We can see here that we overrided the same Parquet file we did before with an empty Parquet file. So let's now, first of all, let's make sure that we fix the table and we can now query. As you can see, yes, we can query the data. We can see only 2011, which is really only version 0 data. So version 1 is actually empty. Let's add the version 1 data again. This is the 2012 year data. And quickly, let's check what happened to the delta log. And we can see here that we have version 0, version 1, and version 2. If we look at the data quickly, we'll see that now we have the full set of data, both 2011 and 2012. The one difference in this case is that version 2 now actually holds the data that our production version holds in version 1. Version 1 is empty. We can find it, we can query the Parquet files, and we can see that they are empty. But it's not as easy to track it as with the version logging. So we have two different versions to track it. Either undo the version and take a big risk of playing with the delta log directory, or we can identify the Parquet files, empty them out in a way by overwriting them with an empty Parquet file with the same schema, and then continue to work as usual. Let's go back into the solutions and review the future solutions.
So now when we know how we can use Delta to fix the disaster recovery might happen problems, let's understand what are the caveats of this solution. First of all, you can only remove the latest version. Don't try and remove all the versions. You do not want to corrupt Delta in a way that you will not be able to use it anymore. So we'll make sure that do it only in DR and do it only for the last version. Make sure you do not cross a checkpoint. Delta collates all the JSONs of the last 10 transactions into a checkpoint. Try not to overcome this problem and not to overwrite a checkpoint and just deal with the JSON files. Before last one, if your last action is delete or an update, the previous version files might be marked as deleted, as Zishan showed us. When you delete, you're actually creating a new copy of the data, and we will remove the old version files. The same happens with update. In this case, you will not be able to undo either the latest corruption version or override the Parquet files. You will have to reinsert the data from the stable last time travel version and execute or update or delete again. And when you do all of those, keep in mind that every disaster recovery has a rollback. And when you go back into your primary region, you might have to resolve the same data corruption. So keep it as simple as possible and try to make sure that you know how to fail back again. As for future solutions, we have two solutions that can become handy. One option is not to rely on your cloud replication. So create a separate process that will copy the data files. Once all the data files arrive, you can now copy your Delta log file. This will create a larger gap between your region 1 and region 2, but this will make sure that every version that lands on your region, on your secondary region, will be completed and execute it, and you'll need know exactly when and which one of the versions you'll have to rerun again. As for the second solution, in Delta, we're preparing a clone replication. And as part of the clone replication, we create a deep clone. Deep clone will do a similar solution and will replicate your data files for you. So you won't have to take care of it. And once the data files will be replicated, only then the JSON version files, log files, will be replicated as well. Making sure that whenever you need to touch your data on your secondary region, it is complete for the last version that you executed. We'll be happy to hear your questions. Thank you very much for attending it. Please don't forget to rate us and review the sessions online with us.